Z load equal 50 ohms, okay, go ahead.
And then it says, what is the reflection coefficient in the VSWR?
Oh, well, they give a length of line at all or not? It's Z naught, characteristic impedance is what?
The Z naught, I guess that's part of it. It's the same part. Let's see. Z naught is 18.6.
No, Z in, you mean, it's 18.6.
Oh.
Isn't that the input impedance? Here, help me understand the problem. Which problem is it, for instance?
It's 3.
Number 3. And go ahead and read it from the beginning.
It says the impedance and propagation constant at 100 megahertz for a T-line are determined to be Z0 or ZL equals
Z0, okay, equals
18.6 minus J 0.253 ohms.
253 ohms, correct.
And the propagation equals 0.0638
0.638.
plus J 4.68.
Okay. Go ahead.
And then calculate the per unit length parameters.
All right, so here's the trick with this one. I think it's in the solutions, isn't it? Didn't I put the
Yeah,
solutions?
it's got the values, yeah. I was just trying to figure out how you got to it.
Well, it really, well, I think it shows you, doesn't it have the solution worked out? No, okay.
No.
Well, take a look at this. What is Z naught, the characteristic impedance? That's the square root of, this is per unit length, R plus J omega L over G plus J omega C, right?
Yep.
That's Z naught. What's the propagation constant? That's equal to the square root of R plus J omega L times G plus J omega C, right? All right, now watch this. This is just trickery here. But you gotta be good as engineers manipulating things. This is just the way it is. If I multiply this by this, what do I get? You see how the J omega C is canceled? You all see that, class?
Mm-hmm.
So if I multiply Z naught by gamma, I'm left with simply R plus J omega L. And those R and L are per unit length. You all see that? All right. Now, what happens if I take this and I divide it by Z naught? If I take gamma and I divide it by Z naught, what happens? Well, now the R plus J omega L goes away, and I'm left with G plus J omega C, right? You all agree with this? All right, now once I've done that, I can pretty much get it, because I know if I take this term and multiply it by this term, I'm left with this, right? So now I'm going to have a real and imaginary value, right? And if I have, to get L, I have to divide the imaginary by omega. Do you all with me on this? And if I want G plus J omega C, or C, now I take gamma and I divide it by Z naught, and I'm left with this, right? G is the real part. If I just take the imaginary part and divide it by omega, we're going to go ahead and get C. Do you agree with that? Let's just get these first two. So can you guys in your calculators, you might as well get them out and use them. I'm going to advise everybody, bring your calculators to class with you. Work out these things when I ask you to, because you're going to find out you're going to make everybody does this. They're going to make errors in their calculations they think they can't make, especially if that characteristic impedance formula, or the ZN formula, where I have Z naught times quantity ZL plus J, Z naught tangent of beta L over Z naught plus J ZL tangent of beta L. Guaranteed, people, half the class will mess it up first time, unless you start playing with your calculators and do it. Can you go ahead and give me this one, anyone?
I think it is.
Well, go ahead and just multiply it out. I just need these, because these values you can enter into your calculators, right? And just recall them and multiply or divide.
It should be 2.37 plus 87.03J.
Plus 87.03.
Yep.
All right, now that means we have R right now. R is 2.37, right? Now, to get L, what I have to do is take this number, 87.03, and divide it by omega, which is 2 pi times F, and F is 100 megahertz or 10 to the 8th, right? And then that will give me L. So go ahead and, if you just take 87.03 and divide it by 2 pi and multiply that times 10 to the minus 8. what do you get?
Uh, 1.38 to the negative 9.
All right, what are the answers?
The R is 2.317.
All right, somehow we missed the best. We're close. I don't know. Did I put something down wrong?
Wait, never mind. It's 2.37 is what I got on my calculator.
All right, then you can check that one. What about L? Is that right? Sure.
L's right, yeah, it's 138 million.
You follow me? Now, if you want G plus J omega C, you take gamma and divide it by Z naught. That's it. And I thought that was laid out there. It's not?
No, it's just the values.
It's in homework 1,
Oh.
this solution.
See, I
Yeah.
thought, I'm sorry. I usually I cut all the solutions and I put them in one section, then I reference them further on. All right, you all see what's going on here?
Mm-hmm.
Any other questions about this one? Did they use that reflection coefficient
Yeah.
at the load?
At the
All right.
impedance.
So if they want the reflection coefficient at the load, didn't we cover this last time, class? Right? So what is that going to be? It's simply Z load, right, minus Z naught over Z load plus Z naught. And we have Z naught right there, and we have Z load. Now, I'm going to tell you the way you always render this. Give it a magnitude, show a magnitude of gamma L, and then have it at an angle. And the angle, you better put it in degrees. You can put it in radians if you want, but make sure you state RAD, or else sometimes the calculations get messed up. People think it's in degrees and it's really in radians and vice versa. What do you get for this one, the reflection coefficient? Do it in your calculators. I'm telling you, people mess this up. You won't believe how they mess it up. I said, Dr. Baginski had the right formula, but you have the wrong answer. So it obviously means you don't know how to do a calculation. And as engineers, half of the job is doing it meticulously. You're good bookkeepers. A lot of people get really sloppy. And you know, when you're sloppy on a job, especially a multi-million-dollar job, it costs the company a multi-million-dollar. So don't get sloppy.
0.458 at an angle of 0.625 degrees.
0.458 and an angle of, say that again?
0.625 degrees.
0.625 degrees. Basically, it's just about at 0 degrees, all right? Which means it's about strict real. See if you guys get that. By the way, I don't see that when I look at that, but it could be. Anybody else? What'd you get, Josh?
Same thing.
All right, well, because the minute I see something like this, a real and imaginary, well, that imaginary is pretty small. I'm starting to think I'm gonna have a fairly decent angle, but I could be wrong and I am here. Any other questions about the homework? We went and we did the entire complete circuit, right? So we got it, and this is something you better listen to me now. Like for Friday, if I give you a problem that has a source voltage, I'm gonna make one up here, we can work it together. Say I have 10 volts here, and say it's at an angle of 30 degrees at a frequency of 10 to the 8th hertz. That won't matter that much, except for one reason. I'll have RS equal 50 ohms. Then suppose I had a cable, and I allowed this cable to be not in wavelengths, but in meters. Let it be 3.5 meters. And then I'm going to put a load resistance here of 25 plus J25 ohms. And I have a characteristic impedance equal to 50 ohms. And I want you to tell me what the load voltage is, plus or minus V load here. Let's do this in class together. Now, this is the complete circuit. There's one caveat. Here, I gave it at an angle. So I want the voltage here, both magnitude and angle. Does everybody follow me on this? What's my first step to doing this problem from last time? I gave you a problem like this, didn't I? All right, what's the first step? Anybody? I don't want to pick on you only, but you have a beard, so you're more of a target. This guy has a beard too. What's my first step? All right, what's your first name again? What?
Gains.
Gains, all right, Gains. Oh, what's my first step? What's your first name? What's your first name?
Andrew.
Andrew, I'm gonna try to learn your names this way. What's my first step?
My name's David.
One out of two things, right? You got a first step for me?
Trying to find it.
What's your first name?
Randy.
We're gonna learn the names and nothing more. All right, man.
Find the impedance of the load line.
That's right. And what is your first name?
Duncan.
All right, Duncan, you are correct. So what we want is Z in right here. So Z in, don't worry, Josh, you're not out of the loop yet. What is Z in? This is the formula you have to know. Well, any takers?
Z naught,
Right, Z naught times,
ZL,
right, ZL plus J
Z naught,
times tan of what?
EL,
Beta L, beta, over
Z naught,
plus J, right, times tangent of beta L. This is one you gotta know. This is for the lossless case. The reason you know is it's lossless, there's no angle here. 50, there's not a plus J10, it's 50, so it's real. That means it's not, it has no loss. All right, that's the input impedance, right? Now, I didn't say this, but suppose the velocity on the line, phase velocity, is C, or 3 times 10 to the 8th meters per second. So phase velocity is that, right? What do we need next? Please pay attention to this. Beta is equal to 2 pi over lambda. Almost always put beta in terms of lambda in this equation. Then figure the length of the line in lambda. And that way you would put beta here is 2 pi over lambda times the length of the line in lambda. Maybe it's 4 lambda. The lambdas cancel. You got that, everyone? All right, so that's beta. We need lambda. What is lambda? If the velocity on the line is the speed of light. Anyone? How about, what is your first name?
Jared?
Jared, can you tell me how to calculate the wavelength?
I can.
And what is your name?
Reagan?
Reagan, can you tell me how to calculate?
No.
What is your first name?
I'm Josh.
Can you tell me how to? I've had you. Can you tell me?
Ivan.
What, Vince, did you say?
Ivan.
Ivan, do you know how to calculate wavelength on that line? It's velocity is the speed of light.
Is speed of light divided by phase frequency.
All right, C over F for this one, because it's lossless, just C over F. And what's that? 3 times 10 to the 8th, right? Over 10 to the 8th, or it's 3 meters, pardon me, 3 meters, isn't it? With me, class? Now, if it's 3, follow me how I got it? It's lossless. So normally to calculate wavelength, or to be exact about it, you know that wavelength times beta is 2 pi, and you take 2 pi over beta. But we don't have beta. We're putting beta in terms of wavelength. So we can also default to the fundamental formula where you go to gamma is equal to alpha plus j beta, right? And that's equal to the square root of r plus j omega L over g plus j omega C, or for a more, well, I'm gonna just stop there. I wanna get on with this problem. It's 3 meters, do you agree with me? Beta has several forms, we went through that. All right, now if it's 3 meters, correct? Because the reason we can do that is because it's phase velocity, it's the speed of light, and it's lossless. Now, what's my next step? I should get the quantity beta L. And so beta is 2 pi over lambda, right? Now I want to put the length of the line in lambda. Now think about it. L that I gave you is 3.5, right? But we're going to put it in terms of lambda, so we divide by 3 meters lambda, and that will give me the length of the line in times lambda. So it's 3.5 over 3.
something really gross. Something really gross.
Not gross. It's what is it? It's 1 point, is it 05 something or?
1.166666.
That's fine. 1.1666 repeating out, that's fine. So now I multiply this by 1.666 lambda, and the lambdas cancel. And now you can take 2 pi times 1.666, and what do you get? You got it right there, right?
7.33.
And that's radians. It's probably 3333 radians, right? Now go ahead and find the tangent of that value, because you're going to use it again. Tangent of that value is what? It is in radians, remember, not degrees. Because beta is radians per meter. This is the kind of problem you gotta do backwards. You should know every aspect of it. Go ahead. Just the tangent.
1.74.
So you got, okay, 1.74. I'm telling you the best way to do this. The reason I say that is because you see how you got tangent beta L here, tangent beta L here. So store that, all right? When you do this calculation. Trust me, this calculation people mess up all the time. And on quizzes, I generally don't give hardly any partial credit because they're based on that week's homework. So you gotta get the exact answer. Don't write a formula and say I should get half credit for that. No. You gotta use the formula. Now, when I have that, now you go in and I've got Z naught here is 50, right? I've got ZL is 25 plus J 25. Put those in memory. You have many memory slots, right? So put 50 in one and 25 plus J 25 in one. And then do the calculation. What I suggest is you do this calculation first, store that information, then do this calculation, store that information, then bring it back and divide, and then multiply by Z naught. Now, I'm going to show you, you're going to get a lot of weird answers here. Go ahead, people, and tell me what you get for this calculation. I tell you, I know what I'm talking about. I've taught this course plenty of times, and this is one of the things. Engineers bobble this one sideways.
What's ZL? Is it 25 plus J 25?
Yes, let me write that in a way that's more apparent. And by the way, if somebody sees an eraser yell at me, this is 25 plus J 25. Got it, Josh? Or not?
Maybe.
What I suggest is do the top one first, then the bottom one, then divide it, and then multiply by Z naught. What I see is people trying to load all the things in so they can do, you don't have any HPs around here, do you? Everybody's got TIs? Well, HP is reverse Polish notation. You keep on loading in the thing you want to use last first. And then you do the calculations like you would in, you know how you do it in machine language? First in, last out type deal. Y'all know that. All right, what did you get, anybody? Josh, why don't you give me yours?
130.2.
I'm sorry, 130.2 at an angle of what?
Oh,
Well, can't you go to polar?
yeah, I can.
Give me it at an angle.
It's gonna take me a second.
Isn't there just a
Well,
130.5,
130.5, go ahead, at an angle of?
negative 0.067 radians.
7 radians.
Yes.
Can you give that to me in degrees too?
At -4.
Minus 4 degrees? Is that right? No, radians are 50 something, 57 degrees, right? Try that again. Is it 0.67, did you say? Right.
0.06.
Oh, 0, no, then I believe it, then he's right. Minus 0.067 radians, or minus 4 degrees about, is that right?
yeah.
Yeah, that's about right.
That's right.
Okay, and that's in ohms. That means now we do this. We take that circuit, and the first thing we need to do is this. We need to go ahead and start here. I have a voltage here at 10 at an angle of 30 degrees, and I have a resistance of 50, don't I, class? And now, that goes in to where the transmission line is. And what we do is put the Z into the transmission line here, and we get this voltage. Plus to minus, this is V line right here. So tell me what that is. It's what? Voltage division, isn't it? It's just 10 at an angle of 30 degrees, right? And then it's multiplying Zn, that we just calculated, over Zn plus 50 to go ahead and get VL. And give me VL in terms of a magnitude and an angle, please. Are you going to thank me? I'm doing this with you. Because if you haven't worked the homework by now, and I know how to do this one fairly quickly, you're gonna have a lot of work in the next couple of days for that quiz, because we've covered a fair amount of material and you have to understand all of it. Ivan, you have it?
Not yet.
You look disgusted. You got it?
Yeah.
All right, give it to me.
7.23 at 28.9 degrees.
0.9 degrees?
Yes.
Okay, that's one. Believe me, they can be different. You all get it? See what else other people get. Doesn't matter more, it teaches you how to use your calculator. Did you get it?
Same thing.
You got that? What'd you get?
I don't think I got that. I just.
You understand what we're doing right there, right? We're just taking 10 at an angle of 30 degrees, and we're multiplying it by Zn. This is Zn. And you're dividing, or then you're gonna divide it by Zn plus 50. Right? This should not be a troublesome calculation on your calculators. But if you haven't operated on your calculators a lot and used them, it is. Now go ahead and do it again. Try it. Because this should be quick. It should be that fast. I think you're right. The problem a lot of times is entering the degrees or radians in a polar number. People aren't used to doing that, so you have to figure out how to do it on your calculator. Or you can just calculate that first with that equation and then store it, and you've got it.
Mine's just a little bit off.
By what?
7.22.
All right, I'm gonna guess that's a rounding error. That probably had to do with the number of sixes or something like that. I'm not worried about that. Same degrees though, angle?
29.9.
That's close enough. All right, are you with me, class? So now I take that, and what's my next step? That's the voltage right here, just on the other side, just inside here. Now what do I do? Anyone? Reagan, what do I do?
What else were we looking for?
We're looking for the voltage here.
Oh.
So now I've got the voltage right on this side of the line. What do I do? Anybody know?
Do you do another voltage division?
Now we equate it to what? You're right. I say this voltage, right, is the voltage on the line. That's this voltage is equal to V0 times E to the minus J beta Z, right? Plus V0 plus. Actually, it's this. It's equal to V0 plus times the quantity E to the minus J beta Z, right? Plus the reflection coefficient times E to the plus J beta Z. You all remember that equation, right? This is the equation that describes the voltage at any point on the transmission line for a lossless case. Because it's J beta Z, it has no alpha. Follow me? If it was lossy, it would have an alpha. Is everybody with me on this one? Now, listen carefully. What is the reflection coefficient? I'm going to put the reflection coefficient over here. What is the definition of the reflection coefficient? We just talked about this. Anyone?
ZL minus Z naught over ZL plus Z naught.
You have to know this one. ZL is 25, right? Plus J25 minus Z naught is 50 over 25 plus J25 plus 50. So what's that going to be? Well, that's minus 25 plus J25, right? Over 75 plus J25. So what's that in terms of a magnitude and an angle? You all with me on what I'm doing here? I'm just defining, I'm finding out what the reflection coefficient is from the definition, the basic definition you need to know. like the back of your hand. I don't give formulas on quizzes and stuff, and even on the exams, I give very few. You get to know these by working them all the time. You gotta work a lot of problems in this class. What do you get for that? Gamma L? It's minus 25 plus J 25 over 75 plus J 25.
-0.2 plus.
No, give it to me in polar. Always in polar.
Got 0.44
0.44, go ahead.
at an angle of 160.
116 degrees?
Yes, sir.
Ivan, is that you?
Yes.
Okay, thank you. All right, can anybody confirm that or deny that?
I got some.
Same thing, everybody? Did you get the same thing, Liz?
Yes.
All right, I wanna make sure everybody's learning how to use your calculators. Got it? All right, now, I've got that, so I've got this, right? Now listen to me carefully. What is the value, where do we typically put the 0 point in our coordinate system if we're doing a finite transmission line? At the low, this is 0. This means this point is z equals minus L. Got it? Because it's minus L, the signs on these change. So now I can say that VL is equal to V0 plus, and it's e to the plus j beta L. Well, we have beta L over there, right? On the top right. And it's going to be that plus the reflection coefficient, which you gave me as 0.44 at an angle of 116 degrees. It's going to be that times e to the j. This would be minus beta L. Now beta L is right here, and it is in radians. This is in degrees, so you're going to have to make sure you change them appropriately. Now that's what V0 is, I mean what VL is equal to, but we need V0. So what do we do to get V0 plus? We simply take VL, and that's VL. We take VL, and we divide it by e to the j beta L plus 0.44 at an angle of 116 degrees times e to the minus j beta L, and we get a value. And give it to me in magnitude and angle, please. Now, if you didn't work the problem, you're getting a first chance, I mean, you're getting you might say a chance to redeem yourself, to make sure you know how to do this. And you gotta know how to do all aspects of this and be very familiar with it. Y'all following me what I'm doing here? Got it? To get V0, I just take VL divided by that stuff. Now what is V0 gonna be? Can you do this calculation for me? You got VL here, and this beta L is up there, so it's e to the j beta L plus 0.44 at an angle of 116 degrees times e to the minus j beta L, which is up there. Anybody? Now you can see how long it's taking you to do these calculations. This is for one problem. You should be able to get through a problem like this in about 10 minutes max. And that means you're fluid with your calculators and you know how to do step by step. Because this is an easy problem relative to some of the ones that will be coming your way. Any luck? You get it? You're not even bothering, huh? Trust me, try it. I mean, on your calculators, do this stuff. You don't have any idea how much time I'm gonna save you if you work here. Because if you don't know how to punch buttons now, with me laying it out for you on a test, or a quiz, you'll really fall. Did you have a number or not?
No.
All right. Ivan, you got it? What's the problem?
Yeah, E.
This is simple. Turn this into radians right here. Just 1/16 into radians, and go ahead. Now that's e to the j, whatever it is in radians, right? Take that and subtract beta L from it, and then put it up here as e to the plus j that. Right? That's the easy way to do this. This is usually the part I think people are going to get stung by. They're not sure what to do with that. Good. What you can do if you're having trouble with this part right here, I'm just guessing. What you can do is take 0.44, that's going to be the scalar value in front of it. Then it's going to be taking e to the j 1/16 over 180 times pi, turns that into radians. Follow me? Take that minus beta L. Beta L's up there, that's 7 point whatever it is over there. Y'all see that? Then you're going to have just magnitude 0.4 e to the j radians, right? You can stick that right in there and add it to just j beta L. And then add those two together, then divide it into VL. And VL is this. You should be able to do this efficiently. But I think I'm exposing some of the clumsiness, because on quizzes and stuff, they're about 10 minutes. And this is a typical quiz problem. Very typical. So, can you give me that answer? Anyone? Yeah. Do you have it or not?
Something.
Well, can I have something up here?
Yes. 6.167 volts.
Give me the angle.
136 degrees.
136 degrees. Possibly right. You're going to get a range of answers. Anybody else got anything? Anybody? I can crack this open on my laptop and do it fairly quickly in MATLAB or MathCAD. I'm just wondering, did you get that? Anybody else confirm this? Well, for the sake of time, I'm going to assume that this is the correct value for V naught. You can check that. It shouldn't be that hard. Now, once we have V naught right there, remember that's magnitude and angle. That's not what I wanted. What I actually wanted was the voltage at the load, right? So how do I get the voltage at the load? All right, look, this is the general equation for voltage on the transmission line, right? We just calculated V naught, didn't we? So where is the load in terms of Z? So we would put in 0 for those values of Z, and now you would see that the V at the load would be V0 plus, and it would be 1, right? Plus the reflection coefficient. Right? Your reflection coefficient is 0.44 at an angle of 116. Therefore, what is VL going to be? It's this value V naught, if it is correct, 167 at an angle of 136, do this with me, degrees, and then it's times 1 plus the reflection coefficient, 0.44, and it's at an angle of 116 degrees, or, pardon me, yeah, 116 degrees. And when you do that calculation, what do you get for VL? Magnitude and angle.
5.5 at 162.6 degrees.
162.6 degrees. Volts, and that's a peak voltage. Now, if that's the voltage at the load, how much power is deposited by the load? This is one right out of circuits, right? If we have a voltage across an impedance, what's the power?
Voltage over the impedance.
Well, let's make sure everybody follows me on this one. This is a peak voltage here, 5.5 is a peak voltage. Now, to get power, average power, it would be 1/2 the real part of V phasor times I conjugated. You all agree with me there? V times I conjugated, we covered that. All right, so what is I? Well, I at the load is simply V at the load divided by Z at the load. Do you agree with that? All right, V at the load is this right here. So I can say if I take 5.5 at an angle of 162 degrees, and I divide it by ZL, which was 25 plus J25, and that's really going to be square root of 2 times 25 at an angle of 45 degrees, I can go ahead and get that. So that looks like I got 162 minus 45 as the angle. So it looks like it's 117 degrees. And what's 5.5 divided by square root of 2 times 25? Can you just give me this value?
0.156. There's 157.
0.157. It's I think it's 117 degrees,
Yeah,
isn't it?
that's right.
117 degrees, and that's amps, right? All right, now watch. This is 1/2, right? 1/2 the real part of V, that's V, 5.5, and I'm going to go ahead and put it e to the j, 162.6 degrees. And then it's times I conjugate. I conjugate would do what to this value? If I conjugated it, class?
Becomes negative.
This becomes minus 117. So now it's going to be times 0.157, right? E to the minus j 117 degrees. And I want the real part. So that's 1/2 the real part. Go ahead and take 5.5 times 1.5 or 0.157. What do you get? Just 5.5 times 0.157. Those are the real parts, right? I mean, that's the coefficient. What did you get for that?
0.86.
0.86. And the angles you add, so you have 162 minus 117, right? And that's going to be, pardon me? 45 degrees? 45.6?
0.6 degrees.
All right, so that's going to be at an angle, or e to the j, 45.6 degrees. It's about 45, I think. Right. So my final thing is I have 1/2. The 0.86 can come out because that's a scalar. And what's the real part of that? Think Eulers. If you have e to the j theta, right? That's cosine of theta plus j sine theta, right? The real part is just the cosine, right? So isn't the real part just the cosine of 45.6 degrees? And by the way, that is going to be about 1 over square root of 2. So give me the value for the average power in watts. Anyone? No? I'm just looking for answers. No? Do you have it or not? You're very reluctant to share information with
We're
people.
trying to give other people a chance.
They'll have a chance.
I got 0.30085.
I'm sorry, zero, could you say?
0.30085.
30085 watts. That's all right. Did you get that?
Yeah, just that.
Thank you. All right. That's the kind of problem you need to be able to do quickly and efficiently. In all aspects of it. So I could give you like a voltage at the line, and I may want the source voltage, or I may want any part of this problem is fair game, and you have to understand this problem fairly well. This is the complete circuit, but it's a simple circuit. It's one transmission line, one load. That's it. Now what we're going to do today is explore Smith charts. How many have heard of Smith charts? All right, what I'd like you to do on Friday's class is make sure you bring a compass, and make sure you also bring a straight edge and a sharp pencil. I'll bring some Smith charts. I'll even email them to you, okay? And you can print out as many copies as you want. A Smith chart is nothing more than a tool used to quickly calculate impedances, admittances, and also doing impedance matching. So if we have a load like this, 25 plus J25, and we have a 50 ohm line, and we don't want any reflections, we can modify that by putting either in series or in parallel with the load another transmission line with a certain termination, and we can get what's called matching, so there's nothing reflected back. And that's the idea. We don't want anything reflected. It's, we'd like all the power delivered to the load. And that's what we're going to find out about. I'm going to mention one other thing about transmission lines that is useful. I talked about it before. With transmission lines, the goal is to have no reflected waveform, or the reflection coefficient equal to 0. Now there is a trick with transmission lines, and I want to show you this. If I have a characteristic impedance of one line, call it Z1, and then I tie this into another transmission line here. And the transmission line is only lambda over 4 in length. And I have a load here. And I'm going to call this load ZL. But it's going to be strict real. Now my goal is this. I would like the input impedance here, right here, to be equal to Z1. Now I'll show you why. This is a characteristic impedance of a transmission line, right? Here is a load. The goal of this is to have no reflected power. Now when we have anything attached to a transmission line, we don't care what it looks like. It can look like anything, as long as we can represent that as an impedance. You follow me on this? So right here, the input impedance at this point, Zn, would be equal to Z0. Well, Z0 is really this characteristic impedance, and I'll call this Z0. I call that Z1, this Z0, and that's ZL. So it's Z0 then it's gonna be times ZL, right? Plus J times Z naught times the tangent of beta L over Z naught plus J ZL tangent of beta L, right? Now I just reproduced the input impedance equation. Now that's a quarter wavelength long. I made that, and this is called a quarter wave matching. Really, they call it a transformer, but it's a T-line transformer. But you can just say T-line. It's a quarter wave matching transmission line. It's an old trick. And this only works for a single frequency because wavelength is a function of frequency. So if I cut a piece of line like that, and this is really one done more with fabrication. Now what I'm going to do is calculate the value of Z naught right here that I need to achieve this input impedance right here, be Z1. Because if it's Z1, then the reflection coefficient here would be 0, wouldn't it? If you look at this, the reflection coefficient right there is equal to the input impedance, Zn, minus this Z1, where I came from, over Zn plus Z1. Well, if Zn equals Z1, this is 0. And that's what we're going to try to always achieve. We get nothing reflected. We want everything transmitted. That's the goal. So look here for a second. And notice, this is the input impedance that I want equal to Z1, right? Now look, beta L is the key thing. Beta L, if that's a quarter wavelength, beta would be 2 pi over lambda times L is lambda over 4. That's pi over 2, isn't it, class? Right? What's the tangent of pi over 2 going to? It's heading towards infinity, right? What that means is this, when beta L is lambda over, is pi over 2, this whole thing becomes simply Z naught, right? And then it's going to be times a J, and it's going to be Z naught squared, J Z naught squared, divided by J ZL is equal to Z1. Y'all see that what happens is only these two terms remain important. These two terms become insignificant. So we have J Z naught squared, the tangent's going towards infinity. This tangent will cancel that one because they're both racing towards infinity, divided by ZL. You can see the J's cancel. So I have Z naught squared over ZL equal to Z1. And therefore we can select the value of Z naught that will make this work, to make it match. And if we take Z naught equal to the square root of, that's ZL, of square root of Z1 times ZL, that in fact will match that. So there will be no reflected waveform. Do you follow me on this, class? This is called a quarter wavelength matching transformer. When you build microelectronic circuits, or really fabricate circuits on things called duroid, where they're flat pieces of copper separated by a dielectric, what you're going to do is etch. You basically create structures so that the transmission lines on those structures will have an impedance equal to whatever your load impedance is times whatever the impedance you're coming from, the square root of that, and you can easily design transmission lines to meet this goal. So you want the characteristic impedance to be that. This is a trick. It only works at one frequency though, remember, over a small band. It's frequency dependent. Now, for the Smith chart, I wanted to show you that one. This is done in your book. I want you to relax for a second and listen to me. This is kind of a complicated proof. Now, it's laid out in Dr. Wentworth's book, so I don't want you to write stuff down. If you have to, go ahead, but I want you to listen. When we start and we talk about reflection coefficient, we talk about it's equal to ZL minus Z naught over ZL plus Z naught, right? If we divide top and bottom by Z naught, on this equation, we would get something we call small ZL will be equal to ZL over Z naught. So that would be small ZL minus Z naught, or minus 1, pardon me, over small ZL plus 1. If you have your books, you can probably open them up, and how many have their books here? A couple people? You can open them up. I encourage you to bring your books and write in them. I'm going to reference a lot of stuff in your books. And give me the page where this is. I'll tell you real quick. This is the Gang Smith chart. All right, this starts on page 62 of your book, the proof I'm talking about. Now, ZL actually, that's the reflection coefficient. This reflection coefficient has a real value plus J an imaginary value. And ZL has a real value, so it's RL, and it has an imaginary value plus XL minus 1 over RL plus JXL plus 1. So just realize what I've done there. I've broken down the reflection coefficient into its real and imaginary parts, and I've broken down the normalized impedance into its real and imaginary parts. Do you all see this, class? Now you notice this is normalized. It means I took the load and I divided it by the characteristic impedance of the line it was attached to. Do you all follow me on this? Now when I have that, I want you to look at this. Really what I have here is RL minus 1 plus JXL, and downstairs I have RL plus 1 plus JXL, right? I just grouped them in terms of real and imaginary terms, right? I'd like to get this in terms of a real and imaginary number alone. So what we have to do is multiply by the complex conjugate. You've probably heard of this. Down here, this is an imaginary number, right? The complex conjugate would be the real minus J, the imaginary, correct? So if I take this and I go ahead and I multiply it by RL plus 1 minus JXL, and this by RL plus 1 minus JXL, I'm multiplying top and bottom by the same thing. And the reason I'm doing it is now downstairs I simply get the real part, RL plus 1 squared, and I get the imaginary part, plus XL magnitude squared. So this times this renders only this. There's no imaginary part. Do you all see that, class? With me? Now what happens upstairs? That's real, right? But notice what happens. I have RL, and then I have minus 1 RL, plus 1 RL, that cancels, and then I have minus 1 plus 1, or minus 1, correct, class? So I have RL squared here, minus 1. Y'all follow me when I have that times that? Now, look at the next term, the last term. Now I have JXL times JXL, which would be minus XL squared, where the minus sign is plus XL squared. So now I can say this is RL squared plus XL squared minus 1 here. Are you with me? Now, when I look at this next part, I'm going to have JXL times RL plus 1, and then I have minus JXL times RL minus 1. I'm going to do this in terms of plus J, and what I'm going to do is put down this term first, so it's going to be quantity XL times RL plus 1, and then it's going to be minus XL times RL minus 1. Now just bear with me. I'm doing this to make sure you see why this works. Now look here. I have XLRL minus XLRL. That goes away. Do you agree? Right? And then I have XL times 1, and I have, well, let me actually break this out. This is going to be XLRL plus XL minus XLRL, right? And then it's going to be plus XL. You follow me? What do you see happen?
XLRL cancels.
That's right. This goes away, right there. So really, I can replace this whole thing by J2XL. And I'm using that term XL. With me? Now remember, what is this equal to? It's really equal to the reflection coefficient, but I've broken it out into a real and imaginary part, correct? Now listen to me. That means the real part of this trajectory, if I have gamma, the real part, that's equal to, what's the real part of that trajectory? It is equal to this, right here. So it's equal to RL squared plus XL squared minus 1 over RL plus 1 squared plus XL squared. That's the real part. The imaginary part is equal to 2XL over RL plus 1 squared plus XL squared, right? Now, in his book, I want to make sure, in his book, yeah, he's doing all this. This is equation 288 and 289. He does it in terms of anyway, keep that in mind. What he does is breaks it out this way too. He says that when I have reflection coefficient is equal to ZL minus 1 over ZL plus 1, right? But I can just as well get ZL from that, and I can say, if I do ZL, just watch this, I can take gamma L, right, times ZL plus 1 is equal to ZL minus 1. You follow me on that? And when I've done that, then I can go ahead and say, I have ZL times gamma L minus 1 would be equal to let me just see here for a second. All right, that would be ZL is equal to gamma L plus 1 over gamma L minus 1, and you should have that. Oh, I'm sorry, 1 minus, my bad. There's a minus sign there, so it's 1 minus gamma L over 1 plus gamma L here. And that's equal to the real part plus J imaginary part of the load. So now he does this way. I've got these equations for the real part and imaginary part. I'm going to just say one thing about this. These things can become trajectories, or they can become circular circles with a certain center. This way that he does it will show it a little easier. So here he's going to say this is equal to 1 minus the real part minus the imaginary part. So it'd be J over 1 plus the real part plus J imaginary part. And I'm just going to tell you what's going to happen because I'm not trying to use the whole class for this. When I go ahead and do this, I can take this and I can multiply this by the complex conjugate 2. And you'll see this is the real part, this is the imaginary part, so I can multiply it by 1 plus gamma, the real part, right there. And then I can have minus J gamma imaginary part here. And I can take the top and do the same thing where I'm going to multiply this part by 1 plus gamma of the real part here minus J gamma of the imaginary part. Now you can follow this in the text, and what happens when you're done with this, you're going to get equations that can be put in the form of a circle. He does it in his book. I've got to get to one more thing, that's the reason I'm going to stop I'm not gonna break this one all the way out. I was gonna do that one, but I thought to myself, he does it differently in his book. So if I have this, what it amounts to, I have equations for a circle. If I have just x squared plus y squared equals a squared, does everybody recognize that's an equation for a circle with a radius of a? Centered at 0, right? If I have x minus a squared plus y minus b squared equals a squared, I'm sorry, not a, call this b and call this c. Well, this is an equation for a circle as well. But the center of the circle is going to be at b and c, at x equals b, y equals c. Do you follow me? Y'all remember this stuff? Now, with this particular one, I'm just going to tell you what happens. When I multiply all this together, I get a strict real number downstairs. Then when I multiply this together, I'm going to be left with a real part and an imaginary part. When you look at these things, they can be put in terms of that equation. And he does this in 292 and 293. And what these represent are trajectories or circles with a given center. Now, I'll spend more time on that when I have a Smith chart in front of me. But now I'm going to show you something about graphing these trajectories and what it allows us to do. I should have gone ahead and finished that, but I'm not going to have enough time to get to what I need to today. I'll do that next time. I'm going to ask you to read through that proof. It's a more complicated one. You don't need to reproduce it, but read through it. I was trying to show you how it was developed, and I got down to this point, and I'm stopping right here because, frankly, I don't have a Smith chart to actually put up and show you exactly how the trajectories work. But now I'm going to get to the final product, the real Smith chart and the way it's worked. So write this down. This is a Smith chart. Normally, and I have slides on this, but I don't know if I'm going to get to them. Just put a big circle there. Now, go ahead and draw an equator. And next, find the center of this right here. So what you're going to see is this. You're going to see lines that basically do this. You see a lot of them that do this. These are equations to circles related to the imaginary component that have some radius out there that they're drawn about. And then there are going to be circles, but there are going to be things like this also. And if you have your Smith chart, let me just tell you where one is if you have your book. That's on page 63. That's what I'm drawing. Now, I want you to do something. Put at the very north pole here, put J1, and at the south pole, the very south pole is, put minus J1, and draw out one of these circular lines like an arc to that point. Over here, put the point 0, and over here, put the point infinity. Now, all these circles have a radial point that they're drawn about outside that inner circle. What I'm about to show you are concentric circles that do this as well. Start with one that goes right through here, right through the center point. That's a circle, and call that the R=1 circle. And then you'll see circles that do this, that close, and you'll see circles that do this as well. Now, you're going to have to work with me on this. And I want to just take you a second, make sure you draw this up, and I'm going to show you something. All these lines that intersect normally on the outer circle, they are the imaginary component of a normalized impedance. You'll see one at the North Pole that says J1 if you have your books, and you'll see one at the South Pole that says minus J1. And then you'll see values increase here. As you come here, you're going to see like minus J4 or 5 and stuff like this. Eventually, when you get to this point, they go to a value of infinity. Do you have your book? If I have a second, I'll put this one up. Now here's how you use a Smith chart. Suppose I want to know, this is one way. I have the input impedance ZL, and I'd like to know what the impedance is here, Z in here, I don't know, but the transmission line is L long. So here's how I go about figuring this problem out. It has many other uses, but this is one of them. The first thing I do is take this, and I find my small ZL, and I take large ZL, and I divide it by the characteristic impedance. The characteristic impedance of the line is Z naught. Here, I'm going to get two values. I'm going to get a real value, RL, and I'm going to get an imaginary value, XL. I'll write that down. You're with me on this? Now, when you use a Smith chart, and I'm just going to give you an example. This will be an example. Suppose I said my normalized ZL was equal to 1/2 plus J 1/2, or 0.5 plus J 0.5. Here's how I use this. I go in, and all these circles right here will have an R value like of 2, and this will have an R value of 1, and one about here will have an R value equal to 1/2. Are you with me? Now, what you do, if it's a half, you find that circle, and it's going to be a complete arch that has the value of 1/2 on it. Then you find the value of J 0.5. Now J 0.5 will be somewhere out here. It's about, I think, right about here probably. So this would be J 1/2. If you have a Smith chart, can you see how in the outer part you'll see something on the ledger that will have 1/2 on it? And you see this one is 1. Take a look up here. All right. So you find that half one, and then you go to the point where they intersect. So this intersects that, as I'm showing you right here, and that was the Z load. And the first thing you do, the very first point you always put, is the entry point, and label that 1 with a Smith chart. Then you take your straight edge, or your compass really, and you draw a line from there to there, and carry it through and tap this point on the outer edge. When I give you Smith charts, it'll make a lot more sense, but the first time I like to do it just on the board like this. Now, out here you're going to see, at the very outer part of the circuit, you're going to see something that says WTG. This is wavelengths towards generator. What it means is how many wavelengths you have to go from the load to get to the generator is what it is. But you've actually got a point here that you marked out, and you'll be something like 0.27 something. You're going to see what that is. Try to appreciate this. It's like a mile marker on a highway, like exit 57, all right? That's the point we're going to measure distance with respect to. Are you with me? Now, if this line is a certain length in meters, you need to turn it into length in wavelengths. You need to see how many wavelengths it is. And let's say it's 0.3 wavelengths. All right, let's just go ahead and say, for the sake of argument, this line is going to be 0.3 lambda long. So now, I'm at the load, okay? One other thing I didn't tell you. At this point, go ahead and take your compass and you make a circle with that radius centered, dead center in the circle. And what this is actually, I'm going to just tell you this. This is a trajectory of the reflection coefficient. It's the reflection coefficient not just at the load, but at any distance, at any point, L. So at the load, this would be the reflection coefficient. We'll get to how you can measure that directly, or how you can actually figure that out with this. But for now, that's the point that you move to, all right? I mean, this is the point you find the mile marker. Can you all see it's about 0.2 something there? 0.25 is right here. This is about 0.27, isn't it? Just take a look, roughly. Now, if I'm moving a third of a wavelength, if I add 0.27, let's not go, yeah, okay, 0.3. When I'm gonna go ahead and move a 0.3 lambda, what I'm gonna do is this. I'm gonna start here on 0.27, and when I add 0.3 to it, it's 0.57, is it 0.57? Maybe I better pick a better one. Let me go because this is an odd one. Let me go 0.15 lambda. So if I add 0.15 lambda, I have 27 and 15, so that's 2. That's 0.42 lambda, right? That means I start here, and I'm going to egg around the circle, keep going, keep going, keep going, keep going, and right about here, you're going to see a mark that says 0.42. I know this is 0.5 right here, or 0. And now I cast the line. I go ahead and draw a straight line there, through there. And this will be my normalized input impedance right there. This is the second point. Can you follow what I'm doing here? I'm using this like a highway marking system, mile marker. But my trip is going to be only on this arch. So when I get here, I read some values. Now, if you look there on yours, you're going to see something that has a real value that I'm going to just guess is close to a half. It might be a little different. And it's going to have an imaginary value. Do you follow me on this? But the imaginary value is going to be negative. And here's why. All the lines that are like this, these lines that come normal into the circle right here, normally into, these are the imaginary components. If they're below, I call it the equator, they're negative J values. If they're above the equator, they're positive J values. Follow me? Keep that in mind. It's not hard to understand. But now that I have this Zn, I can find the actual value of Zn here by just taking the value of Zn that I calculated and multiplying it by the characteristic impedance. It's denormalizing it instead of normalizing it, or unnormalizing it. And that, in a nutshell, is how I use a Smith chart to calculate the input impedance. Now, there's many, many other uses for it. What I wanted to go through is the simplest possible one. I'm just about out of time. And the reason I don't put a Smith chart up there right away and start working it, because a Smith chart has a whole lot of clutter. If you look at it, it's got all sorts of information. If I can just start drawing the basics and showing it, I think it works better. I want you to read, I'm going to ask you to read that section on Smith charts. I'm going to give you some basic problems. I'll send you a Smith chart. I'm going to ask you to work some of these Smith chart problems and make sure you know how to do all the prior homework for Friday for the quiz, okay? Are there any other questions about what went on today? No? I don't try to make this I feel kind of bad that I didn't have time for that proof, but I never got this out if I did. It is time, is it? Yeah. All right. Do you have any questions?